the flow of water through a terrain, and the little sort of square boxes with holes in are fields, and you set the whole of ball bearings going, or balls going down it, and they settle in the fields. So the farmers who have the fields at the top get lots of water, and the farmers with the fields at the bottom get poor water. And this is typically used by making the farmers who are rich farmers at the top with lots of water play the farmers at the bottom, and vice versa. So it's a model used to get the community to think about how to share water resources. Okay, so it's a workable model in that sense. And you can change the flow and do various things. So this is the kind of thing I mean when I'm talking about workable resources. It doesn't have to be bits of mathematics, doesn't have to be bits of algebra. And the third thing I think one needs is this capacity to reveal. That depends on the technology of inquiry. So I want to say something about the technology of inquiry. For me, it's really quite important that one thinks about this as a technology of experimentation. So it's a form of experiment. The way that models are used, which is for me more important than what models are, is as a form of experimentation. And I'm using Roman Higgs' 1997 account of models as having an internal dynamic given by these workable resources. So if we think about the internal dynamics here, they're the qualities of stuff inside the model that one can ask questions with and change and alter around. But in order to get that project going, you have to have an external dynamic. You have to have a question and a purpose that you're trying to ask about this model. So you need an external dynamic, which is what's going on here if I do X. An internal dynamic, which is the workability of the model, will give you some answers. But that only gives you answers within the world of the model. So there's like a glorified thought experiment with a manipulation of the model. And then there's the really difficult bit: can you make inferences from that experiment? Under what kinds of ways can you make inferences? Well, you can make inferences within the world of the model very easily, because you've created this world, you've created these manipulatable resources, and you've asked a question, you've got some answers, and you've got an inference regime inside there. But the big problem is always relating those inferences to the world outside. So it's not that making this an experimental framework gives the answers, it's merely that it gives a way of framing this problem about how you relate the model to the world, is to think of it as fundamentally an inference problem rather than some kind of basic similarity difficulty. It doesn't solve it, it just frames it differently. Okay, so this technology of inquiry that I'm interested in here, and I want to... I completely lost track of time here. I want to just briefly go through three different models to show you this: questions, models, manipulations, and answers. And I've got three models of roughly the same period, one of which is an algebraic model, which is an inquiry into the world in the model, quite clearly. Another of which is a statistical econometric model, which is inquiring really about the world rather than the model. And the third one, which I talked about on Tuesday for some of you who are here, is about a model which tries to be in both domains. This is a really straightforward little model that Samuelson built to understand Keynes's general theory. Well, actually indirectly, because he took it from Hansen. So this is on the top left, the basic Keynesian, Samuelson's basic version of Keynes's general theory into a little model. Y equals G plus C plus I, and then each of Y and I have been, C and I have been further set out. And what he does with this model is to inquire what kind of answers this Keynesian model would give us about what happens if we increase government expenditure. That is, we have a Keynesian policy intervention in this little world, what will happen? And the first thing he does, having got his little model, is to simulate it arithmetically by putting in some maybe plausible, maybe not plausible values for alpha and beta. And I'm not sure whether you can see these numbers at back, but just changing these numbers gets completely different kinds of answers out in these model simulations. So some of them have an increase which then just basically levels out. Some of them create big cycles, some of them create damp cycles, some of them create exponential, off out into the explosive stratosphere. And at that point, he said, these simulations, these experiments, reveal almost anything can happen. You've got this small little standard Keynesian model, and depending on what numbers I put in, anything can happen. And this is not very satisfactory. So he then went ahead and solved the model algebraically and plotted all the solution space according to what kinds of outcomes will happen in what kinds of spaces. So he sort of mapped those possible outcomes into a map of all the possible solutions that you could get. So this is clearly an inquiry into the world of the model, inquiry into Keynes's model, well, Keynes's theory translated into a working object of a model, as to what would happen if you actually did increase government expenditure by 1 unit. This is one of Tinbergen's models for the Great Depression. Tinbergen built the first ever econometric models, macroeconometric models, rather. On the left is his Dutch model in equation form, having been estimated. On the right is actually not from the Dutch model, but from his American model, a chunk of one of these equations showing you what happens over time once it's been fitted. And in the middle, there's a little causal arrow sequence of the time relationships in the model. So what are the questions here? The questions are, how should the Dutch economy get out of the Great Depression? It's 1935, 1936 when he's building this Dutch model. And he simulates the Dutch model to see what the Dutch economy, what the Dutch government should do. And his answer is they should come off the gold standard, and then they would solve their problem. Which indeed they did, but not for a long time, and not because Tinbergen said that, but because Tinbergen was very, very junior. But the point is that the inquiries, the questions about the model, were not questions about how this model behaves like the Samuelson ones. They're questions about what can this tell us about the world, given we've fitted this with statistics, what kinds of things can we learn about the world by simulating it into the future. And this is the famous Fitz Machine, now in the Science Museum in London. This is the scale for those of you who, this is the size of the thing with Phillips on the left and Newlin on the right. It's a large hydraulic machine. And this is an object which is both an inquiry into the world of the model. A lot of the reason for building this was to figure out arguments in macro at the time about the relationship between the accelerator and the multiplier, what the causal structure of investment, what caused investment flows and various interest rate issues. But it was also used to think about what kind of things might happen if you did certain kinds of actions. So it's also a model which was used to tell stories about the real world, to give you insight into the real world, or plausible stories about the real world, as well as to explore different kinds of theoretical arguments. Well, what does the capacity of those objects to reveal depend upon, right? They're very different kinds of objects. They reveal different kinds of things. I think what I want to claim about this is, well, the materials of the model does matter, but that's because different materials offer different experimental resources, right? So it's not that it has to be an artifact or any kind of model, but that these different models had different materials, or have different capacities to reveal things. They're in different forms, and they work according to very different rules, right? So going back, the materials of models does matter to the question that you're going to ask, because the different materials will give different experimental resources and teach you possible things about different aspects of the world. So the materials and the kind of questions you're asking have, in a sense, to line up. You know, you can't really tell sensible questions about particular values of things in the world unless you're in the statistical framework of Tinbergen. But Tinbergen's model doesn't give you many resources to explore Keynes's general theory. It really doesn't, because although Tinbergen built this as a kind of Keynesian model, it's not obvious where the Keynesian model is in Tinbergen's big statistical framework. Right? So it has to be an alignment between these two different things. Does the scale of the model matter? Does it matter that the Newton and Phillips machine is huge and Samuelson's little thing is very small. I don't think the scale matters, but the dimensionality matters. That's the number of dimensions that you've got there, which give you some possibilities. And I'm going to come on in a minute to this other question. How do model experiments compare with other kinds of experiments as a technology that reveals? So we thought about that one. Okay, so the different dimensions. I think one can think about it this way. Every time you've got something in the model that you can alter, that you can vary, is a possible dimension for being manipulated. Right? So if one thinks of Samuelson's little model, he's got two parameters, he's got fictional time, and it's in mathematical form. There's only two things he can manipulate in there. That's the alpha and beta in his Keynesian model. That's what gives him these dynamics, which mean that anything can happen. Tinbergen has something like 16 variables, each of which could be potentially things that you could think about controlling or altering or really investigating. He has real time represented in the statistical form. So he's got, if we count time, this extra 16 plus 1. Newland-Phillips machine has 9 controlling valves and a real time in hydraulic time, but not real time. Each has a time dimension that works somehow to map onto the economy, but none has the real time of the economy, because it would clearly be, well, you couldn't do it, but also it would be useless. It's just like the problem of having a map the same scale as the world. Right? You can't do that, but also it wouldn't tell you anything, because the benefits of maps to reduce the scale so that you can see things. So the time is a dimension, but it's not real time. It's a time which has to also be thought of as a manipulative variable. So if we go back to this this issue, right? It's the dimensions of possible manipulations in here also vary quite dramatically, and those dimensions are part of the machinery. So I don't mean to be mechanistic, but part of the stuff which can be worked with and which will offer potential revealing strategies. So I think the more dimensions, the better, in the sense of the more possibilities for learning when you work with a model. It's not obvious, it seems to me, what kinds of dimensionality you need. If you think about an alternative field, anatomy, a big step forward was to move from anatomical drawings of bits of the body to three-dimensional models of bits of the body, right? And they obviously have different kinds of revealing possibilities. So it clearly does matter for some fields that it's a three-dimensional object rather than a two-dimensional drawing. I think in economics, very often we're concerned with time, forward possibilities of prediction, backwards when we're trying to explain historically why the Great Depression happened, why the financial crash of 2008 happened. And I put in sideways because it doesn't look like that's another dimension, but of course the use of models for counterfactuals is to run the world in another form parallel to the time that we've got. And that's actually one of the things that political scientists do when they're doing their counterfactual thinking. So I put in time as a sideways possibility. And the number of elements that can be varied. So I think they're important. It's relative to the question at hand. I don't think it's always obvious what the dimensionality of a model is. It's not obvious that Tinbergen has 16 dimensions that can all be independently varied. Right? There's 16 variables, but some of them are so constrained by the equations that there's probably not 16 dimensions of variability, 16 separate things that can be varied. Okay, so each experiment then has a different focus of investigation, these three, different capacities to reveal answers, and about different things about the world in the model, about the theories that economists have, or about the events in the world. But I want to move on to this, really the most difficult question, as to how to think about the status of these answers that we've got here. So the reason I want to think about these uses of models as an experiment is because I think it helps to think about looking at the experimental outcomes, not just a final result, but the whole set of outcomes that comes from these process of experiment, not as a correspondence truth problem, right, where the model is an account of the world, what's true in the model clearly is or isn't true of the account of the world, but as an inferential problem, what can we learn about what by these experiments? And here's the sort of way I think about this in terms of other sorts of experiments. And typically the lab experiment has been taken to be the kind of experiment, the kind of classic experiment that forms the boundary. Although I think increasingly in econometrics, field experiments are forming the basic dimension for comparison. Lab experiments typically we think have high internal validity. That is, within the laboratory, one can get very definite results from a lab experiment. One might not, but one can. And the internal validity is based on the controls inside the laboratory, controls inside the experiment, the controls of the environment, and the controlled manner in which the experiment is done. So internal validity can be attested inside the laboratory. But actually it's very difficult to give an account of external validity which will hold in a general way. That is, how do you export your finding from the lab to the world? So this big problem of external validity, which philosophers and economists have been writing about, Francesco Guala, for example, but it really does, it is a problem for lab scientists. So when one thinks about lab science as being the main comparison, one should be aware that actually the external validity problem is not at all one that has been easy to solve or to kind of classify in a philosophical way. Model experiments, internal validity is obviously about the validity inside the world of the model, and for economists that usually means, you know, have you set this thing up to give consistency in a sort of consistent set of answers and to have certain kind of characteristics. I'm going to talk a little bit about that internal validity in an example, but here I think the world, the inference of the world is not an external one, but a parallel one, because it's not as if we've got, in the lab, we've got what we think are the kind of stuff the world is made of, and what we're trying to do is does it work out outside? Is it true externally as well as internally? Well, in the model, you haven't got the real stuff of the world in the economic model. You've got a diagram or a maths or a map or something. So you're talking about not external validity, where you've got the same stuff taken out into the world, but something that you hope is going to happen in this parallel universe. The real world, which might or might not be parallel to your model. External parallel validity are both problematic, and I don't think there's an easy solution to either of them. And I think those both have problems compared to statistical experiments. And the wonderful thing about statistical experiments is not that they're necessarily always informative, but they're set rules for internal validity and external validity. Right? It may not be easy to get them to work, but the statistical framework is about creating inference rules about what you can infer from the sample and under what conditions you can infer from the sample of the population. That is internal and external validity. And they're both framed within the same statistical theory. So statisticians have a much neater way to think about these things because they can think about both of them in their setup that they already have. Although it has to be said that although they might be really clear in terms of thinking about inference regimes, they may not be sufficient for action, and demography is a wonderful example. Demography is very descriptively effective, but it's not one that you can go and causally intervene with. Right? Demography is going to tell you how many school children you're going to need schools for in 5 years' time, but it's not, you can't use the demographic laws to go and change the birth rate. Right? So there's a sort of limit on what they can do. Okay. So back to the qualities. Okay, I've talked about manageable small representations, miniaturization, compression. I've talked about the resources for investigation. I've talked about dimensions and capacity to reveal. And I want to come on to this last point, which is the most difficult to get to work, about this representative quality that Dastel and Galison suggest that we need. How are we going to pass out justifiability as typical or exemplary in some form? What makes a model representative in some form for something? So in order to think about this representativeness, one needs to think about the class of things for which this is going to be representative in order to frame the inference space to the class of things that the model is going to be representative for. So models typically not going to be saying something about everything, but models are very often specified to be representative of a particular subpart of the economy. So a class of stuff that is in the economy. If that can work, if one can get that to work, I mean if, not philosophically, but if you're an economist practicing this thing, right, what you're going to get is something, an inference possibility which is wider than the experimental one, right, because if you've got your experiment to work in the lab and you want to know whether it works outside, you may have to take it to lots and lots of different places to figure out whether it works outside. Right? Just because it works in the lab doesn't mean it's going to work anywhere, and just because it works one place outside doesn't mean it's going to work everywhere outside. So the model experiments, I think, have a somewhat wider range than the lab experiments, but they're much weaker validity. I mean, if your lab experiment works in the lab, you take it outside and it works in place X, right, then it's a pretty strong place X inference. Right? So it's going to be more particular and stronger for lab experiments, and model experiments is going to be weaker because this bounded place is not, as it were, real stuff that we can take from the lab experiment. So representativeness is going to give us possible inference range, which is wider than labs, but quality, which is less valid, weaker. So the inference range is associated with the typicality of the work